very good. About the proceedings, actually, I can start from this point. Since NATO asked us, suggested us to prepare something in the NATO series proceedings, after this meeting, I will try to contact you, and if you would like to contribute to these proceedings with something written, not only oral, we will try to do this kind of things together. We need a little of help, but I think we'll be able to do it. Okay, I have prepared, my name is Rita Cuccihiara, I'm from the Department of Ingegneria dell'Informazione. I'm an engineer in computer engineering, University of Modena, Reggio Emilia. And with Naftali, we are the organizer of this small project funded by NATO. This is the agenda of my talk. As Tali suggested, it's very informal, so please stop me whenever you want. After a very short presentation of my lab, I will present you what the BSAFE project and the goal, and then I will spend the other part of my time to present some of the work of the project. Then Andrea will present one specific research activity, but since this project in different way during 3 or 4 years produced a lot of things, I think that should be interesting also for you to give an overview of what we are doing in video surveillance, and especially which kind of data we have that we can share with you if you would like to continue with this work. My university in Modena, Modena is in Emilia-Romagna, in the red part of Italy, you see, and it's a very old university in Italy, especially for economics, for medicine, for math, and for physics. And in the last 20 years, we created also the Faculty of Engineering, of course, with sponsorship, very important, because Modena is the city of Ferrari, Maserati, Ducati, and many other mechanical giants. But apart of this, we have created this engineering faculty, not only for mechanics, but also for computer and electronic engineering. And within our faculty, we have my lab in image and video analysis, and since a few months, actually, we have created this new center that is called SoftTech ICT, that is more devoted to ICT for enterprises, and that has been sponsored by European Community and Emilia-Romagna region. And it was a long story for me to create this small lab because it's not very easy to work with company every day, but now it's something that is concrete, and I am very happy for this. And we have some money for doing not only technology transfer, but especially research and industrial research for small and medium enterprise companies. Because in my region there are more small companies than large one, but in ICT there are very elastic and very flexible and very enthusiastic to work. So I hope that should be a good adventure for us to work in this part. This is my group. Now we are 5 staff people, actually 4 because Andrea is moving in a few days at the University of Venezia, but I think that he will stay around for a long time because he's still involved in my SoftTech Center. And we have some PhD students and some postdoc, as well as a very small spin-off working in industrial computer vision. What we are doing with these people, especially we started with some expertise in computer architecture, especially for porting algorithm in embedded system, in CPU-intensive system like now in multi-core and GPU. But in the last 10 years, we was working more in computer vision and pattern recognition, especially for object people in event recognition. Now I have a PhD student that is working in 3D people analysis, and we study in the sense we use classification clustering method applied for data set of images and data set of video, and we try try to work also in the area of content-based image retrieval and natural interface for multimedia. The typical applications, since we are in engineering area, so this part is very important for us, is especially in surveillance and security, so, and also in part of forensics, meaning data mining in video archives for supporting investigation, and especially in the last 7 years in people surveillance. We are using also RFID and other sensors together with cameras for sensor fusion in security, and instead the thermal, high frame rate, and multi-camera was used for telemetry in Formula 1. We have some application in multimedia retrieval for artistic images and for medical images, and other things that you can understand are related with computer vision. These are instead a brief overview of the project we are involved with. Okay, Be Safe is ending now, and also this is a European, a small European project that I'm coordinating with other universities and some companies in Europe about surveillance. I cited here also video that was a project, a very interesting project coordinated by Arnold, where I was subcontractor of them. And then we have some projects that have been funded by Italy and by our region especially. All of them are in people surveillance in such a manner, or a part of this one that is for embedded computer vision and the cultural heritage. And I would like just only to underline this project that is a video surveillance as a service. That is a project we are doing with IBM in Italy and with the Lapida region. So in this period with IBM, I sent some PhD students in US and with the Steve Russo group, and now we are working with their library too. Okay, finally, just to give you the presentation of my lab, this is the other thing I'd like to underline. After a big video adventure, we created this open advisor portal that is an open repository of video surveillance. We have not only video, but all of video are annotated for trajectory, for posture, for identification, and so on. So this is something that if you would like to use to share, you are welcome, because we have some data, and we will be very happy if there is someone that would like to try to use this kind of data for machine learning or many other things. And okay, and the last thing important is that we have an international PhD student in ICT that is not so common in Italy. And for this reason, also I would like to say that if you have some students that would like to share with my university, we will be very happy to try to do what we are doing with other universities, and should be a good occasion to collaborate together. So this is something, these are some images of some projects that we have developed. For instance, this is a park in Reggio Emilia that I will present you, and there are part of posture analysis. That one, there is not the video, unfortunately, but it's for smoke detection. That one instead, in the middle, was a forensics analysis for video surveillance, for something that police got me for doing analysis of this, and shadow analysis and other parts. If you would like to have more information, of course, I will be able to do. Okay. Instead, some words about the project. It's a very long story, as you see, because as Dali said at the beginning, John Ratchville phoned me because I met him in London and say that we could do something together, putting together machine learning and computer vision for surveillance. I say, yeah, we can try. So we actually wrote the proposal in 5 years ago, and then was accepted, and we started 1 year after. because NATO, you know, it's very long to decide. But in that time, Joel told me that he moved from university, and so he was not able to use this money. And so I asked him to suggest me someone else in Israel, and for this reason we was very, very happy to meet Sally for this kind of things. Of course, we changed a little the project, so we spent a while for understand what we was able to do together. So we asked for an extension of the project and an extension of an extension, and now we are at the end of this. And actually this project is a part of a program that is called, at the beginning it was called just only Science for Peace. Now it's moved in Science for Peace and Security. And this is a project, you can, I put here the page, in the web page, because maybe if you are interested you can find every information here. It's very easy to start to prepare this kind of proposal. There is a continuous proposal. Now I know that has been evaluated now in October, so the next time will be evaluated in March. And you need one NATO country and one friend of NATO country, so Israel or the other Mediterranean countries or ex-Russian countries or something else. And what you have to do is to propose something that is related to science, but with a possible future application in the field of peace and security. So we actually, NATO was very collaborative with us, also for preparing the proposal and for everything, and so was I think it was a good adventure. If you would like to try again, I'm available to do that. And but at the beginning, this was the consortium. Now we changed this consortium in such a manner, and also the end user, because it was easier for me to work with some end user in Italy, especially Bridge 129 is a small company, but is doing video surveillance in Italy, and IBM initially is not doing surveillance, but try to use the IBM system, so we are collaborating with them. And the project motivation was very ambitious because it was about the possibility to understand the behavior of suicide bombers. And this is something that Joel actually told me, because I was not so expert in this area. But after the first idea, we decided just only to look about visual feature that can be used to understand abnormal behavior and abnormal action. Look at that, this work is something that we proposed 5 years ago. So maybe 5 years ago, this was actually a research activity, very, very creative and new. Now it's something that after 5 years, there are so many people are working in this area that the improvements are very effective. And so I think that now not only research, theoretical research, but also applied research in this part. The goal was just only to put together computer vision and machine learning for video surveillance. So this was the generic goal, applied possibly to prevent crime, terrorism, and security threat in public place, and with the research activity in extracting visual feature and in real time, possibly, to detect people behavior and to use some machine learning. And this is something that we did this year with the strong support of Sally. Just to suggest to continue the discussion of Sally, unfortunately, the NATO support gave a lot of money people from not NATO countries, and especially for hardware and software, more than for other things. But this is no bad, so we can actually use also this money in settlement. The result of this project, I start with the result and then I can show you something about this. At the end, we produced some scientific results, because we produced some papers in journal, a lot of papers in conference proceedings, especially in AVS healthcare, advanced video surveillance conference. I will present you something about this. And we did some workshop in Modena, also with Naftali. I'm working also in military academy that is in my city, so we are working with them, and we presented the work of Be Safe in many different conferences. So I think that from the scientific point of view, this project was not hard. So I'm satisfied for this, even if I started in this. The activity and the results are related to 3 different topics. The first is people detection and tracking in multi-camera system. Before extracting feature, you have to find people in order to extract that feature. So we're working a lot in tracking, especially in multiple overlapping camera, but also in moving camera and in detecting people from images and videos. This is something that Andrea will present after. And then we especially studied the problem of trajectory. So we are working a lot in trajectory analysis, in space, speed, and shape, and also a small part in action analysis. Then the final part of reasoning on trajectory using standard clustering and classification techniques, but also using spectral graph for detecting anomaly with something that for us was absolutely very interesting. So now I spent a part of my time, and I would like to present you something in this point. I hope, unfortunately, I will be a little superficial because of there are so many things, but I hope that you can ask me something if you're interested to give me more detail. Have you some question for the project or for my presentation now, or some comments?
You mentioned databases.
Yes.
These are all available online, or?
Part of them, especially the video, are just available. You can go to www.openvisor.com and take here the video you want. And then we have other databases that instead are not there, but are absolutely available.
But especially this is raw video, or it's labeled video? Or?
Labeled, annotated with. Well, not so many, because they are not terabyte and terabyte, are 200, 300 of videos, but or maybe more, but are annotated in many different ways. We use annotation system, Viper, created by Larry Davis a lot of years ago, to annotate all the frame in order to extract the concept. Part of this is the result of video project. That we annotate a lot of concepts in general, and then also people and maybe the position of them. For instance, we have a new one that we will present in the multimedia conference in 1 month, that is about people identification. So we have video with people with 3D taken by different point of view in order to do identification. So if you want, we will be happy to share them. Other things, or okay, something. No, I can see this. This is our image lab leads from surveillance. Actually, it's more than 10 years that I'm working in this area. So we created many different pieces of tools in order to work together. And so we have part for segmenting and tracking by static camera, by inverted zoom or moving camera, and especially for people tracking. Then we created something for consistent labeling for multiple camera with overlapping point of view. And then we added many pieces for annotating and detecting the trajectory, shape, some part of face, for face obscuration and face identification, and there is the part of annotated video storage, that one that I told you. And part of this has been done in this project. In particular, I spent some works for the multiple camera tracking. We started with a very basic algorithm of single camera segmentation and tracking by background suppression. There are so many now. We have proposed one approach 8 years ago, but there are so many other. And we use background suppression and appearance-based tracking in order to extract single images. I don't know how many of you are in the field of people tracking and people detection, or if I need to spend more part, but this is something that is standard now in video surveillance to detect people by difference with respect to a background that has been created and modified during the time, and use a prediction of the motion of the people and of the appearance change. With in our case, we are using we model each pixel with a Gaussian and in order for every part of the blob, and use this for tracking during the time. The problem is that when you are working with a single camera, your point of view is very limited, and also there are a lot of problems about occlusion, and so we try to extend this in multi-camera systems. What we are doing, we put together geometry, but not all geometry, but also statistical inference in a Bayesian framework. In particular, we created a homography and epipolar geometry to extract information from the environment, so without initial calibration, but with a sort of automatic calibration. And then we track each people from each single field of view. And then we put together all the information with warping the main axis of the people in the other point of view with the Bayesian inference. I can give you some details, maybe. Okay, this is too much details, and I don't want to lose the time here. But there is an offline initial part, and then on the online process. In the offline part, we use a people as a probe. So in installed cameras you have without any other part. We ask the people to go around, supposing that the people stay in the standing position and walking around, and using these people as a probe, we can create what we call entry edge of field of view. This is a work that is a modification of initial proposal of Mubarak Shah and others in his lab, and one of my colleagues was there for his PhD program, so we started to work together. And after this initialization part of the cameras, we are able to extract something that you can see that is a graph that connected all the point of view of the camera in order to understand where there are the points that one field of view is shared with the other one. This initialization is very important because we can create a homography in this case, and also to extract the epipolar line for the head of the people. Then
this is done by 3 cameras?
Yes. This is an example of 4 cameras we have together, but in the example are just only, in this example are just only 2, I think. Yes. You see, this is the part in my university. There is one camera that is looking in this direction, and the other one that is looking in this direction. One camera is here, one camera is here. There is a panel zoom instead, and another one here. So after this initialization, you can create a homography view like this one. What you can see, this part, central part is overlapped by 2 cameras, and the other part instead is not overlapped by the other. And you create a graph that say when you pass from one to the other. So each camera processes the video independently. For instance, in one time, what you can see here are the people that are detected and tracked by every one of them. So whenever one people is in an area that is shared by 2 or more cameras, the problem is to understand if it's the same people or not. In case of a single people, it's very easy. But in case of crowd and situation of more people together, the problem is that one single tracking system can detect a group of people together, but instead looking for another point of view, you are able to disambiguate this kind of things to understand that there was not a group of people, was a group of people, not a single one. So we use this information to detect the presence of group. So the online process is something that you can see here. When you detect and you track one people, not only at the handoff, so when you pass it through, but in every point, and this can happen because, for instance, you have a group of people together, then one starts to go in another direction, so people is detected. In this case, the consistency resolver starts. What we are doing, we are created a Bayesian competitive framework. That means just only that you start with some prior. The prior you have is, you can see there with, I have not a lot of time, so I'm sorry if I show you in this very informal manner. When you have a new people like this, you can suppose that could be one or the other one. And so your prior is dependent if the group of the other people are together or are alone. If many people are close each other, the probability you have to have a group is higher than the probability to have a single one. So the distance each other is something that you can see here, just only to fix the prior. So this new could be more easily the number 90 than this other that are together. So after this prior definition, you can do something like this. These are two different views of one. You start with the support point in the ground floor, and you project by the homography in the other direction. Then you create the axis that intersect the epipolar line in this manner. So you find if this axis overlaps in such manner the blob that you have in the other part. This is a forward probability, then use the similar things in the opposite direction, and use all of them in order to understand what is better or what is not, in order to, for instance, to see that there's a new one that has not been detected before, which one of this could be the number 3 is the more probable of the other.
So you do iteration forward, backward, all the time?
Just not iteration. We do in one direction, then in the other one, and you put together in a Bayesian framework in order to see if there is enough correspondences both times. Sometimes you can see that the problem maybe we have not detail for this, but the problem is that to understand if which camera is correct. For instance, one see one only people, the other one see 2 people. So which one is the correct one? And so you use backward and forward in order to see what is more probable. If it's more probable there are 2 people or 3 people, it's more probable that it's just only 1 people.
So this is an offline process?
No, it's online.
It's online?
Absolutely online. Look at here we have just only some data that are in the PAMI journal in 2008. This is actually the work, the PhD work of Simone and with also Andrea. And just to give you an example. This is now we are doing this in real time from 2 or 3 cameras. So whenever people is passed, all the people are lined and computed in the other direction, and this Bayesian framework understands there are how many people and which one are the people that are computed. So this is an example with 2 cameras, and this is an example with 3 cameras. So people of the same color, of course, have been detected as the same.
So can you elaborate a little bit what's actually being calculated?
Okay, of course, I can use the other one. That may be easier.
Yeah, I'm sorry.
No, don't worry. I'm sorry, because
for
my point of view is I can. Okay, here. I try to.
from video to PowerPoint all the time.
Okay. So each camera works independently and do tracking, segmentation and tracking. So this is the output of one camera and this is the output of another camera. So whenever one people is here, and this is in a part that is probably overlapped with another camera, we project in the other camera the support point, that is the point where there are probably the feet, and also the people are line passing through the head. And so we projected this in the other direction, and also backward from one camera to another, from one camera to another. If we have three cameras, with three cameras, and then we put together in a Bayesian framework with the prior that I told before, in order to detect if there is a possibility to say that it's the same person or the two person.
So each labeled person here
so this is the number 0, and this is number 0. This is the same of this one. This is the same of this one. The blue one is the same of this one. Is that because you see they're similar? There are different point of view because it's a symmetric area. But for instance, okay, the last time, what you can see. This is the what you can see.
Press the loop there, it will go forever.
Okay. What is the loop?
This one here.
Yeah. It's true. Okay. So in this manner, whenever, for instance, you can see this one is not visible from the other camera because in the other side. So in this manner, we can use this information actually to extract trajectory or to extract information about shape, or to then you can extract all the data you want when you have this kind of things. This method works with 6, 7, 8 people. Of course, when you are crowd situation doesn't work anymore, but in a typical situation like this, it's working.
Because I'm just trying to focus here and maybe give some food for the discussion later on. This is more or less the state of the art in people tracking in such an open area.
There is a new work of Pascal Foix that is similar to this, that has been published in the same year in PAMI, that is very similar, but use another method, of course, and there are so many, because I think Arnold is working on tracking a lot, and there are I think 2 papers on transaction paternized machine intelligence every month about tracking. But this is what I can say is stable enough. We are used in many different situations, not only in our lab, but also in the public park, as I can show you here. This is another a real application, because this is a park in Reggio Emilia where the camera was installed at the beginning. And so also in this case, we are using real time, and it's still available. So, for instance, you can have some errors like this one that are considered 2 people until they start to divide. So at the beginning, you can have.
So you say that 1 until they divide.
Yeah, this is 1 until they are divided. Okay, this is.
I'm just trying to see what are the limitations here. So when there are too many people who overlap, the system.
But,
and when the conditions, let's say light or
what I can say is that you can use also other tracking methods. So this consistent labeling is independent of the type of tracking you are using. So, for instance, I can give you another example. This is a new one because after your lesson of spectral graph, Dalia and Simone are working in adaptive learning of appearance for spectral graph. And what we are doing is that here is not using motion, but only people detection, and in order to cope with the strong overlap. And so this is another totally different approach. So there is no motion. This is something that Andrea will present after. It's just only people detection. And at each frame, the people is compared to many other in order, what you can say here, this is an example more complex. So the system detects every people, but I would like to track Michele, that one. And since it's based just only on appearance, with the transductive learning, and the spectral graph that learn the different aspects of the people clustering different aspects of the same people, he's able to follow him also after very long occlusion. And also, in this case, in more crowded situation like this. This is something that...
So we know that occlusion like this is usually a big problem.
Yes, this is one of the big problems.
How is this solved here?
In which one? Because there is not motion. At each frame, every people is affected. Every people is compared to everyone, and so the most probable with this kind of affinity graph you can see here. So you have more example in transductive learning. You learn more example and you put in your knowledge. And these are the people that are detected at each frame and are compared with all the other one. And so you can decide which is the one. So this is a totally different approach, not based on background suppression, but also in this case, if you want, you can use then consistent labeling in order to use.
So you do essentially an exhaustive trying to match everyone with everyone and see which one is the most likely to be there.
Yes, but in each frame you will be able to detect 20 people, like in a crowd situation. So you have 20 people that are compared with the data set you have in the frame before. So it's not so heavy to have in real time. But we use spectral graph in order to understand, to update the model. This was the initial model, and then the model, if maybe a people change his point of view, so you have different aspects of this, you can use it.
But you don't use any continuity assumption. If someone disappears and reappears a second later on the other side of the picture, you will recognize him.
Yeah, for this is because we are not using motion. We can put all together, of course. In this example, we just only use appearance, this one. So every one of this is compared differently, and the green one is the one is winning. For instance, there is some errors also, of course. So it disappeared. Okay, so he moved, he changed. Look at it changed the direction, changed the appearance, but it's able. This is not concluded work because it's the work of a new PhD student. So now I'm finished my time, and I'm just only on the half of my presentation, so I would like to conclude other things, just only to show you that using this kind of things, we are able to extract thousands of trajectories in the same area. And so in this kind of things, we can do analysis, behavior analysis, action analysis, or something like this. I have no time, but...
about time. So
No.
We're trying to be strict, but since most people told me that they don't need so much time.
Okay.
I want you to, this is really the interesting part of the story. I mean, I want to lay out the foundation.
No, I'm sorry because, as I told to Arnold before, I asked to Simone to give me some detail of the work, and he gave me hundreds of...
This is really important because I'm going to elaborate on what we try to do with this data.
Yeah.
I want people to understand the data, and I think that the issues here are really the critical issue I want to take later. Occlusions, discontinuity in
actually,
time.
the problem we have is that since of occlusion, since of noise, since of many illuminance changed, since reflectance, since a lot of things, what you can see is that this is easier trajectory to extract when there is just only one people. But instead, for instance, one problem we have is that one people is detected for a while, then it's lost, and then it gets lost, and then is detected again. So one problem should be to learn if these people was the same that was detected before in another point of view, in another... So I have another student, for instance, that is working in 3D in order to understand something. But the problem in learning is absolutely open.
So this is one issue that we definitely want to discuss later. What can be done about this type of discontinuities or occlusions or crowd? I mean, how can we deal with so many people together?
So if we applied our system in crowd situation, you will have a lot of very short trajectories that are not connected to each other. So in this example you see, we just filtered the short trajectory. So these are 1,000 of long trajectory, but we have a lot of small parts that are not related with each other. So this is the interesting. Just to give you an example, we can extract trajectories also from other point of view, like for instance, in this case, from detecting the anomaly in the car, in this kind of things. We have the availability of this data if we find a manner to do something.
Can you prevent accidents of the track?
No, this is just how to win a Formula One race that in this period Ferrari is not the first one. So this is something that we are working with them. So this is, so this is all the work we did with them. And they actually are using our tools during the race in order to look at similarity and to look, for instance, similarity between shots and so on. So this is a small interface that now they are using to detect the situation there. Okay, trajectory analysis. Some hints. What you can do with this kind of data? You can detect which is the most frequent behavior, which are the trajectories that have some specific shape propriety, or which are the trajectories that share some specific location and speed proprieties, or people retrieval, who did this kind of things, and what's happened maybe when an open problem, for instance, is the interaction between people. Why two people we can see that they are interacting with each other because they're in a similar place in the same time, or because they are doing similar behavior also. And we have actually all type of data, not only the trajectory but also the shape. So in this case, what we are doing, we propose an approach working using trajectories as a sequence of angles. Why sequence of angles? Because sequence of angles you can find similarity by shape and not similarity by trajectory. Like for instance, say that all the blue one are people near the bench, smoking a cigarette maybe, or the people that are passing through, or people that are going this direction. This was a simulated example at the beginning. This is, for instance, something that we extracted after processing. That there are, of course, many people that are passing through. There are some people, the red and green are because are different directions. So also the direction can be preserved. And this blue are similar to that blue, that are people going in this direction and coming back. So they are doing the same things here. So just to give you. We developed an approach to represent the trajectory with the space transformation. So starting, I can give you an example. We start with the sequence of angles. Then we represent this each trajectory with a mixture of von Mises distribution, because maybe I have an example here that is easier to understand. So each trajectory is represented with optimization, after an optimization of parameters, with a mixture of, for instance, 3 von Mises distribution. And then we use this because after this transformation, we can code each trajectory as a sequence of symbols, where each symbol is one of the selected von Mises distribution. And after this, we can use many algorithms of time series comparison in order to compare them also with different lengths in order to understand the similarity. So what we are proposing, we can do the same not only for shape but also using Gaussian to detect position. And we use a global alignment to align the trajectories that are of different lengths. And at the end, we use Bhattacharya distance because it's easier to use this kind of both for Gaussian and for von Mises distribution. And at the end, just only, we use, in this case, we use k-medoids to cluster together trajectories that are similar. I think that the result was very convincing. For instance, this is an example of what you can find with position and not with shape. So we can collect them by position, or we can collect them by shape. I'm sorry. This is an example. Another example, another data set where you have a trajectory in this direction. Instead, this one are anomalous because they are in a cluster with very few examples. And also, we are doing this kind of things in real time. So, okay, this is another example and the other type of representation with. At the end, for this part, we created a demo system that, okay, sorry if I have a lot of things. We use the same things.
Before that, sorry,
okay.
and take a few more minutes.
Thank you.
I think this is laying
No, but just only because I don't want to take time of the other one. No, the interesting thing is that we use the same approach exactly for trajectory, for measures, representation, and so on, to code and look similarity about shape of people for action analysis. So we extract from each people this kind of images, that is the historic images of the motion of the people. You can extract this integrating during the time the motion, and we represent each shape with a mixture of Gaussian. Each part.
It's in 2D or 3D?
In this case, in 2D.
2D.
This is the problem, because in 2D the point of view is very important, and so you cannot recognize people taken by different point of view. So this is a strong limitation of the approach. But just only to try to use the same approach for different type of data. And for instance, in this case, you can see that the blue part is the part that is not moving a lot. The green part is the part that is moving a lot, and this part is the legs that are moving more and more. And using this kind of information, we have a very simple, actually, a data set, but is available with drinking, walking, jumping, abandoning objects, sitting, and many other. And this method is absolutely perfect with this very, very small data set. Of course, what I can see, this is a strong limitation. The strong limitation is that it's the motion and the activity. It's very dependent on the people. So my manner to put an object on the ground is different to yours, and so maybe that could be used for biometric identification, maybe, and not for. But it could be a good thing. So, to concluding, we have also demo. That is, we presented at CVPR this year. This is working in real time about this. This is another data set that is from Edinburgh, from other data, not our data. And at the end, we can also do re-identification of people and say, this kind of people that is interesting for me, where is 1 hour before or something like this. But I don't want to spend time for this. So the last thing instead is something that is linked with the work of Tali, and I think that you are talking about something similar tomorrow, that the time series can be also represented by graphs. And so what we tried to do is to take a time series of the trajectory and transform that in a graph, describing the probability of a person to move in a certain manner from one area to another area. And then, having a graph, we can use Laplacian filtering to detect anomalies. This is an example of what we are doing. Maybe you can say by the image. We start with a fixed division of the image in parts, and then we use histogram of position of people in order to define the probability of occupancy of people in a certain area. And then we extract, maybe it's not easier to see there, but a Voronoi cancellation in order to say which is the area that are more probable, which are the area of that. And with this kind of cancellation, we can create a graph where each node is the transition between one position to another, and each arc instead is the probability to do another movement after this movement. So the motion from this area to this area is node that is connected to by arc to other possible motions, and then we extract data from our data set and also from other data sets in order to extract the trajectories that are very different to the other one. This is another example of anomaly detection where in this data set you can find that ones that are different to the other one, or these are other examples of trajectories that in such a manner are different to the other one. Okay, stop. My presentation, of course, was too long, as usual. But I just would like to put on the table 2 or 3 different things. The lesson learned in this project, in this activity, the first one is that we cannot use just only geometry, but we need absolutely all the knowledge coming from machine learning, pattern recognition, statistical, to infer information that we cannot extract by geometry only. And we cannot only work on a model basis, especially in people detection. You can not only have a model-based part, but we think that the perceptual part is the perceptual inference are very important. From the other side, we also need the time and the effort to create prototype and data set in order to work with, to understand something of this. What's next? I would like to learn what must be learned in complex environment. It's very often also talking with the final user, they don't know what is interesting. So learning not only the anomaly, but also the second point, learn by normality in visual data should be very interesting for us. This is the only part I would like to put on the table. Okay, thank you.
Thank you. All right, so thank you very much for this really illuminating introduction. I specifically gave Rita a little more time because I think that
3 minutes, that's all you gave.
This is what she took, I gave her more.
I took the police 30 minutes ago.
The reason is really that I think she laid down the critical, interesting questions that we are going to address later on. It was really this combination of statistical techniques coming from machine learning with the challenges that are raised by video surveillance, actually I would say by vision in general, and which are quite amazing, and the fact that we are not doing more work of this type is to me a big surprise, saying what I said before, that there's so many good people on both sides for such a long time. But so we are going to, Rita mentioned it very briefly at the end, I'll say more about it tomorrow morning. How do we actually take video data and turn it into something which I can build, which is sequences of symbols or graphs or statistics that is more common to machine learning. This is to me a really interesting and still open question to our extent, and then apply all sorts of tricks and more or less clever from machine learning to one-class learning, anomaly detection, what do you mean by anomaly in general, predictive models and so on. These are things which are going to come up later on. I'm glad to see that some more people came and hopefully even more later on. There are people here from really entirely different communities. People who are doing industrial work in IBM, for example, or people who are doing language analysis, text analysis, and speech analysis, machine learning in various ways, neurocomputation. I really hope that you can see the connections, and I want to encourage you to raise questions, especially on those boundaries and open issues. This is really, as far as I'm concerned, the main benefit of this workshop is to somehow link those rather beautiful techniques that are available to Rita and others in the computer vision community with the real issues that those who need to do or want to apply clever techniques to real data in various places can raise. So I really want to encourage all of you, those that I know personally and those that I don't know, to raise questions, and especially to Oded, who should summarize it somehow at the end of the day. And tomorrow we are going to do more or less more of the same, but with a little more focus on the theoretical issues of machine learning. So really, it's an open, informal workshop. Now, two questions that I need to settle early. How many of you are interested to join us for dinner tonight? I mean, we can essentially have a reasonable size of group, but so far I know only about especially the speakers. Of course, all of you are invited. I don't think that all of you will come. But how many, besides the speakers who are obviously here, want to stay here for dinner? No one. Okay, think about it until more or less 12. And then I need to finalize with this. It's not only a dinner. I also promise an interesting tour of the city, but for those who don't know Jerusalem by night. This is something I really need to know before noon.
Using your 4x4, right?
Yeah.
No, so you're going to walk. But this is supported by NATO, but on the hospitality of NATO, you have food here, both now and during the last time. You ordered probably more than me, that I was expecting here more people. Please eat as much as you can.
Dali, just to tell you, this is another example of computation that I would like to put here.
Okay.
That is similar things. You can detect all the information about the speed and the behavior of people in this part.
Okay. So you have, let's say, 15 minutes of coffee break.